All right, so this is meant to be a quick review about electronegativity, right? So basically the principle or the strength of which an atom or element likes to pull on electrons in a covalent bond, right? So the goal here is just to give a quick review so that when we start thinking about intermolecular forces, we can gauge the strength of the polarity of a bond and from there deduce how strong the intermolecular forces between similar molecules or different molecules is. So recall that in a covalent bond, electrons are often, in a covalent bond, electrons are shared between two atoms, right? So in the example here so far, up to the top right, is just diatomic chlorine, right? So that's two identical atoms of chlorine sharing a single bond between the two atoms. So that, there's a pair of electrons in there, aiding in helping keep those atoms together. And in this example, the distribution of electrons between these two identical atoms is even, right? So if we kind of look at our color coding here, in the middle-ish is yellow around 0, so there's no uneven electron density over our whole molecule, whereas if we look far to the right on our scale, we get very red, where it would be electron rich or closer to a very negative charge. And then over here on the left where it's blue, electron poor, where if there's a lack of density of electrons, you would expect to see a partially positive region of a molecule, right? So again, this is an even distribution of electrons across that single bond between two identical chlorine atoms, right? So as we discussed in class, this isn't always necessarily true, right? So we would consider this a non-polar covalent bond because there's even distribution of electrons around the molecule, and essentially because these atoms are identical, they're both pulling on atoms with the same strength, right? However, we know from class that doesn't always occur. So here we have an example of a polar covalent bond between one chlorine atom and one hydrogen atom, right? So chlorine has, again, what we would refer to as a higher electronegativity, so it has a stronger pull of electrons than hydrogen does, right? Chlorine has a lot more protons in its nucleus, so it's got a lot more pull. It's got a different orbital structure around its nucleus as well in terms of density of electrons and shells. Meanwhile, hydrogen just has a single proton, a single s orbital, and doesn't really have a very strong pull on electrons. So there's a few things that go into play when considering electronegativity. If you review periodic trends from previous classes, that might help you get a better gauge on where the strength of electronegativity in atoms lies. So again, here we have one chlorine atom that's pulling strongly on all the electrons. Essentially the one electron here from hydrogen, because that one electron from hydrogen is involved in the single covalent bond between these two atoms. But chlorine's pulling strongly on all the electrons around this orbital, leaving chlorine relative to hydrogen, electron rich, so more negative, as you can see from the color coding again, and leaving hydrogen slightly electron poor, making it slightly more positive. All right, so that would leave a large negative, again, negative electrostatic charge around chlorine and a slightly positive electrostatic charge around hydrogen. You may be thinking, well, how does this come into play with other types of bonds? So if the difference is great enough in electronegativity, we actually get what we refer to as ionic bonds, where chlorine wants to pull on the electrons from that sodium so strongly that it actually rips that electron off of sodium, gaining a full partial or a full formal -1 charge. Whereas sodium wants to pull so weakly on that electron, it's more or less happy to give it up, right? So if the difference in electronegativity of the two atoms that are bonded together is strong enough, you can actually have an ionic bond instead of a covalent bond. But we're going to focus on the covalent bonds here on the next page. So here is a chart, periodic table, representative periodic table of the electronegativity of various atoms on the periodic table, right? So when we look at electronegativity and try and determine whether a bond is polar or not, we can use this simple cheat sheet over here on the bottom left, right? So in order to determine if a bond is polar, all you have to do is take the electronegativity of the more electronegative atom that's sharing a covalent bond with another atom and subtract it from the less electronegative atom sharing that covalent bond. Right, and then there's a few different regions of this to consider. So if the difference in electronegativity is less than or equal to 0.4, we would consider that a nonpolar covalent bond, right? So if we look closely over here at carbon, who has electronegativity of 2.5, and we subtract hydrogen's electronegativity, 2.1, that would leave us 0.4, right? So that would be considered a nonpolar covalent bond. Whereas if we go up, right, so 0.4, if it's greater than 0.4, but less than 2.0, we would have what you would refer to as a polar covalent bond, right? So that would be a bond, say, between fluorine over here with a 4.0 and hydrogen with 2.1, right? So the difference there is 1.9. So it's not quite polar. Oh, well, sorry, it's within the range of polar. Excuse me. It's within the range of polar covalent bond. And then the last one here, again, like I mentioned in the previous slide, if the difference in electronegativity is so great that it's over 2, we would consider that an ionic bond, right? So many of the halogens over here, if they were to bond with many of our alkaline metals or alkali earth metals, we would see an ionic bond, right? And that should be relatively familiar to anyone who's been discussing salts in class. So let's move to the next slide and observe some practice problems, right? So up here on the left, we have representative covalent bonds between two different atoms, right? So oxygen and carbon, chlorine and calcium, nitrogen, sulfur, oxygen, silicone, etc. So go ahead and pause the video and go through the practice of calculating the electronegativity difference between our atoms here. And remember that you have to take the electronegativity from the more electronegative atom and subtract from that the electronegativity of the lesser electronegative atom, right? So again, go ahead and pause and give that a go. It's just simple subtraction, and I will animate in the answers. So go ahead and pause if you're all set, right? So if we look closely here, so our first one, oxygen and carbon, the electronegativity of oxygen is 3.5. The electronegativity of carbon is 2.5, right? So 3.5 minus 2.5 equals 1. That falls within our range between 0.4 and 2. We would consider this a polar covalent bond, right? So in this covalent bond, oxygen is pulling much more strongly on the electrons that it's sharing with carbon, making oxygen a little negative and making carbon potentially a little positive. If we go to our next one, right, chlorine and calcium, this should be stirring something if you're thinking about it, right, in terms of salts. So chlorine has an electronegativity of 3, calcium has an electronegativity of 1, so the difference there is 2, right? Again, if we consult our range, 2 or greater is actually ionic, right? And that should sound familiar because we've dealt with calcium chloride in lab before, right? Or if you ever salted your driveway, more than likely you've probably used some form of calcium chloride. So again, go ahead and go through all these different atoms, check your math, and try and start to take a mental note of which bonds are polar and which bonds are non-polar, right? With more practice, you'll get the hang of this, but you can always default back to the basic math here to determine if something is or isn't is or isn't a polar bond, right? If you have any questions, feel free to shoot me an email. Otherwise, please be ready to apply this to our discussion of intermolecular forces, because remember, the electrostatic attraction between polar molecules is much stronger than the mostly non-existent electrostatic attraction between non-polar molecules. See you in class.